Welcome to Let's Get to the Marks, going through some reactions and different synthesis reactions here. So, kind of like organic synthesis. Let's go. Acrylonitrile can be used as a starting material for the synthesis of butane 1,4-diamine, as shown in this reaction scheme. So, you've got reaction 1 involving hydrogen bromide going to isomer W, which seems to have a nitrile and a bromine atom on. We've got reaction 2, which has a nitrile on each end, and then reaction 3, which ends up with an amine on each end of the molecule. So the first question, 4.1, is use IUPAC rules to name isomer W. Okay, so for 4.1, first of all, it's got 3 carbon atoms, so it's going to be propane. You start with the main chain. How long is it? Then have a look. You've got a nitrile. Why have I put that as carbon 1? Well, because nitrile groups, things like carbon dioxide, carboxylic acids, aldehydes, nitriles, they always have to be carbon 1 because they can't fit on any other carbon. They'd have too many bonds. So we know it's going to be called propane nitrile. Now we just need to check out this bromine atom and see which number of carbon it's on, and it's on the third, so it's going to be 3-broma propane nitrile. We could call it 3-broma propan dash 1 dash nitrile. Okay, 4.2, reaction 1 produces a mixture of W and 2 other isomers. Draw the structure of the 2 other isomers, explained by considering the mechanism of this reaction, why all 3 isomers are formed. So first up, going to draw out our starting molecule, which was propanitrile. Okay, so you can see here 3 carbons, we got a double bond there. And so we have HBr, which the hydrogen is going to be delta positive. In AQA, they're not so big on you showing this, and the bromine is delta negative. It's been polarized because the bromine is more electronegative than the hydrogen. What happens is a pair of electrons from the double bond will leave the double bond and go to a hydrogen, but the hydrogen has options. It could form on either of these 2 carbon atoms. Now, the bromine hydrogen bond will also break, as hydrogen can only form 1 bond. It's basically like a group 1 element. And so a pair of electrons will go to the bromine, leaving us with a bromine ion, but we'll come on to that later. So what I'm going to do now is I'm going to go through the 2 different possible products here. This is a 6 marker, so we need to explain it all, that can form. And this is the intermediate that forms when the hydrogen from the hydrogen bromide joins on. And this is the intermediate which is created in the formation of the minor product. And the minor product is going to be 3-broma propanitrile, the one we drew above. That's the minor product. So this carbocation, where you see the positive charge on the first carbon, is a less stable formation. This molecule is the carbocation, and the positive carbon is the one there, the third carbon there. So this is a less stable formation because it doesn't have any alkyl groups. Now, when you're thinking of alkyl groups, you're thinking of methyl and generally ethyl groups, side groups. What these side groups do is they donate electrons to stabilize the carbocation. Those electrons are sort of donated, or an electron cloud moves towards that positive carbon atom and stabilizes it. So it's much more likely to form if you have alkyl groups attached to the carbocation. Remember, the carbocation is the description of the whole molecule with the positive charge. Lovely jubbly. So, what we want to do here, I'm just drawing that in red just to show you the hydrogen has already attached there. Now let's do this second, the major product. This is the one more likely to form. And it's more likely to form because the intermediate carbocation that is formed before the bromine joins on, the intermediate has more alkyl groups attached. And you see here we've got a CH3. That CH3 is a methyl group. And that methyl group is electron donating or electron feeding. It donates its electrons towards that positive carbon atom on the carbocation, and it stabilizes the carbocation, making it more survivable, more stable. Okay, so it means it's much more likely to form. And that means that you're much more likely, because when the bromine ion attaches, you're going to get 2-bromo propanitrile. And this is going to be much more common because the carbocation, this carbocation is the more likely one to form. So you're much more likely to get 2-bromopropane-nitrile than you are 3-bromopropane-nitrile. The bromine atom equally likes these. It's just attracted to the positive carbon. It equally likes these. But what we're saying is that the first carbocation, the one on the left of the screen, is much more likely to form. So if 90% of the carbocations that form in the intermediate phase are on the left, you're going to get a lot more of those 2-bromopropane-nitrile. Okay, so this is going to get you a whole bunch of marks because what we've got here are two isomers of W. Okay, really the minor product is the one above is W, and then we got this other version of W where the carbocation is different and more stable, and so you get 2-bromopropane-nitrile. So we've got 3-bromopropane-nitrile and 2-bromopropane-nitrile. They're two of the three isomers. So where does the third isomer come from? So we're looking at where does the third isomer come from? The minor product on the right here is the one above. That is W. That is 3-bromopropane-nitrile. This second one here, the major product formed, is going to be 2-bromopropane-nitrile. So where does the third isomer come from? Well, it all is all to do with the 2-bromopropane-nitrile. If you look at the 3-bromopropane-nitrile, can you find a chiral carbon? And you can't, because all of the carbons don't have 4 different groups attached, whereas the 2-bromopropane-nitrile has a chiral carbon, the one I've put a star by there with the bromine, the nitrile, a hydrogen and a methyl attached. And if you have a chiral carbon, 4 different groups around a carbon atom, then you can make non-superimposable mirror images, otherwise known as optical isomers or enantiomers. So totally up to you what you call them, but they're going to be looking for that keyword in the mark scheme. And that means that 2-bromopropane-nitrile then has 2 optical isomers of itself here. So this is where we get our other isomer. And basically it's going to form sort of a tetrahedral structure. And you just need to put the CH3 at the top, straight line to the H, and the Br and the Cn, one going in and out. Now you can choose any ones to do this with, as long as you can use any groups in any position, as long as your 2 are mirror images of each other. So you can see here, the only difference when redrawing this is everything is swapped around. And there we go. That's going to get you all of the marks for showing the enantiomers and explaining why they form, because we have the chiral carbon on 2-bromopropane-nitrile. And so that is why we end up with 3 different versions. Okay, let's move on to the next question. So for 4.3, you can see they've repeated the reaction scheme here. They've got the whole reaction scheme repeated, and 4.3 says identify the reagent that is warmed with isomer W in reaction 2. So looking at reaction 2, we're going from the 3-bromopropane-nitrile, and we're going to a molecule with a nitrile group on each end. So what's happened? Well, a nitrile has been substituted for that bromine. It's like a nucleophilic substitution. So the nitrile has been substituted there. Now, what is a source that you know of nitrile ions? What's our source? What would we use as a reagent to get some nitrile ions? Because you can't just get a beaker with or a bottle of nitrile ions. So you would need potassium cyanide or hydrogen cyanide. We'd actually use potassium cyanide here. Hydrogen cyanide's a little bit dangerous. Or sodium cyanide we could use. And we need them dissolved in ethanol. And there we go. Those are our reagent and our conditions. Now look at the next question. State the reagent and the reaction conditions for reaction 3. So we're going from these 2 nitrile groups, one at each end. What's really happening? Have a look at the diamine below. So you can see we've got a diamine below. Look what's really happened. It's got the same number of carbons. There's 4 carbons, but it's had hydrogens added. And in fact, it's got 4 CH2. So it means that the 2 carbons with the nitriles must have 2 hydrogens added to them. And then it's telling us that the nitrogen atoms have got 2 hydrogens on them. So actually, what's been added in this addition reaction? Well, we've added 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Atoms have been added, or 4 hydrogen molecules. So the reagent we need for this is hydrogen, and you use a nickel or platinum catalyst. We use this in the hydrogenation of alkenes as well. to make alkanes. So you probably remember that one. Okay, now for the reaction, it's dead easy. We just got to copy out the original formulas and then just balance it. They just want you to basically acknowledge that there's 4 hydrogen molecules. The rest is just copying it out, the reactant and the product, whacking on the 4 hydrogens that you need. And if you count again, you've got 2 hydrogens on each amine and 4 times 2 on the CH2 in the product. That makes 12 hydrogens. And then if you go to the reactant, you've only got 4 hydrogens, 2 CH2s. So you're going to need another 8 so that you have 12 hydrogens on each side. And there we go. That's how you get your 2 marks. Right, let's zing to 4.5. So for this question, they want us to work out what X and Y is. So how much X is there and how much Y? We're dealing with butane 1,4-diamine and hexane dioic acid. There's 5 of each of them, and they're saying, what is X? So how many molecules would you get if you combined 5 of the left one of the butane 1,4-diamine and the hexane dioic acid? I'm going to use A and B. So if you have 5 of A and you have 5 of B, you can only make 5AB. So the answer to X is 5. And then when we look at Y, what is Y? Y is a molecule of water, and that comes off in a condensation reaction when any of these molecules or any of these polymerizations happen. So all I need to do is add 5 A's and B's and all the bonds and then count how many water molecules have come off. So let me just count out 5 A's. The A's stand for butane 1,4-diamine and the B's hexane dioic acid. They're the 2 reactants. We got 5 of each. So just to make sure I've got 5 A's. Yes, I've got 5 A's. I've got 5 B's. So 1 water molecule is going to come off in the formation of each of these bonds. I'm not going to draw them all out. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to get 9 water molecules come off in that situation. So there you go, 2 marks. Boom. Let's move on to the last part of the question. It's 4.6. So figure 6 shows a section of the nylon 4,6 polymer molecule. Draw on figure 6 another section of the nylon 4,6 polymer showing 2 hydrogen bonds between the sections. All you need to do is copy on either the left or the right. I'm going to do it on the left here. You could do it on the right where I put that arrow. Just copy out the same molecule again. You could reverse it, turn it upside down if you want to suit your purposes. Now, I'm just going to copy it out again. I'm a bit sloppy at this on the computer, but there we go. So just make sure that you get it all exactly right, and then just show how hydrogen bonds would form between 2 layers or 2 strands of this polymer. So my oxygen has a lone pair, and that is going to be attracted to the delta positive hydrogen atoms. You don't need to show the delta sign in AQA. And so we're going to get a dashed line. Don't do a straight line because that will be a covalent bond. We can use a dashed line to indicate the intermolecular force we call hydrogen bonds. And it's between oxygen and hydrogen here. So there we go. I could have had the amine groups attaching to those carboxylic groups on the right. I hope you found this helpful. Smash the like, punch up the bell. Let's get to the marks.
You're still here? It's over.